Let's say you are given with this array of integers and a target to find in this array. You need to write a function which returns a boolean, and it takes two arguments. One is the array itself and the other one is an integer target that you need to look for in this array. Now, this function should return true if this target exists in this array and false if it doesn't. So what we do is there's a simple solution. You start from this index, the first one, and look for target at each index one by one, incrementing the pointer or index. So if you find in this process, if you find a target, you return true. And if the program ends and the target is not found, you return false. So what we do is we create a loop for int I equals to 0, I less than array length, I plus plus, and we compare the current element to the target. Now, if you encounter any such situation, you return true from here. Congratulations, you have found the element. And if the loop finishes without us finding the target, we return false. So this algorithm is called linear search, which is a simple algorithm of finding a target element in a given array. Now, this algorithm takes a order of n comparisons to complete this task, which is a lot. If your array has 2 power 10 elements, then it will take you 2 power 10 steps to find a single element, which takes up a lot of processing if you consider large applications. So we have a better approach for sorted arrays. Let's say you have a sorted array. Now for this approach, the array should be sorted. You have to remember this. The array should be sorted. Now what we do is we put a pointer here and we put a pointer here. Let's say this is L and this is R. And we calculate a midpoint. Now we compare this mid to our target, what we are looking for. Now there can be three possibilities. First one is when your mid is the target element. This is the best case you could encounter. And there can be a possibility when your mid element is greater than target. And there can be a possibility when your mid element is less than target. Now the algorithm is when you know that let's say you have found this case. Now in this case you just need to return true from here because you have found the solution. This is the best case to occur. And if the second case occurs, now think about this. Your target is less than the mid element, which means that your target must lie within this range from L to mid minus 1. Mid minus 1, because your target is less than the mid element and this array is sorted. That's why we need a sorted array to apply this algorithm, because it works on this logic. And if the third case occurs, this one, you can be sure that your target now lies from mid plus 1 to R. So what we do is, let's say you're looking for an element and this is mid and this is L and this is R. Now let's say you're writing code for the second case when your mid is greater than the target. So the target should lie now in this range from L to mid minus 1. So what I'll do is I'll pick up R and I'll put it here at mid minus 1, so that now L and R will point to this subarray. So if this case occurs, the second one, I'll update R to mid minus 1. And let's say if the third case occurs, now L should get updated to mid plus 1. If you haven't understood this one, if your mid element is less than target, which means this element is less than the target you're looking for. So now your target should lie from mid plus 1 to R, right? So your L should get updated to mid plus 1. So that's how it works. So let me write the algorithm now. Let's say you have a function and you need to return a boolean, and the function takes two arguments. One is the integer array, which should be sorted, and a target, what we'll look for. Now what I'll do is I'll create two pointers. One is L to put at 0 at the beginning of the array, and other one is R, which I will put at array.length minus 1, which is the last index of the array. Now I'm going to do some operation. So L is here and R is here. And whenever you see that you have two pointers from both of the ends of the array marching towards the center, in general, the condition we apply to stop them is while L is less than R, which works well because L and R should not cross each other. Otherwise, we will end up in an infinite loop. So what I'll do is I'll calculate mid at each iteration, and I'll calculate this by using L plus R by 2. Now I'll compare this mid element. I'll compare this mid element to the target. If it is equal to the target, then I will just return true from here. Else if the case occurs when your target is smaller than your mid element, then it should lie in the left half of the array, so the R should be updated to mid minus 1. And the remaining case is when your target is greater than your mid element. Now in this case, your target should lie in the right half of the array and L should be updated to mid plus 1. And if in this whole process and the loop finishes and you haven't found your element, so you need to return false, and it means that the target is not there in your array. So this is binary search algorithm. So what binary search do is it reduce your search range by half after each iteration. So if you had an array of size n and you make one comparison in binary search, now your search range will get reduced to n by 2. And after next iteration, it will get reduced to n by 4 and so on. So your program can take any number of steps to solve this problem. In the best case, it can take only one step when your mid element is the target. But we are interested in worst cases. Now let's say in worst case your program took k steps to solve this problem. Now n by 2 power k should reduce to 1 if the problem is solved. And from this relation you can find out that number of steps that your program took, which is k, is equal to log base 2n. So in the worst case, the number of steps binary search will take to look for an element in a given array is going to be order of log base 2n. If your array size is 2 power 10, it will take 10 steps. So this log base 2n is a huge reduction from the complexity of order of n, which was of linear search. So let me show you an interesting application of binary search now. Now let's say you're given with this matrix and you need to find out a target in this matrix. And the matrix size can be anything, let's say n cross m. So if you apply linear search in this, it will take order of n into m steps to solve this, because you have to look at each position in the matrix and compare that your target to the current element. So we need to get better. We need to apply binary search in this. So let me show you a very interesting algorithm which is based on binary search and used to search in 2D matrices. So what I'll do is I'll start from here. I'll start from this position, the upper right corner. And what I will do is I will compare the target that I'm looking for to the current element ij. If I have found a solution, I'll return true, of course. And if the rest two cases occurs, if the target is greater than our current element, what I'll do is I'll move to the next row. Now remember, we have a sorted array here. So if the current element is greater than our target, we can be sure that our target lies in the next row. It's not in the current row. But you might say that we might lose if we are looking for 10 in this case, because we are directly moving to this element and we are not looking at these elements, because these can be greater than 7 and can be our target. Yes, of course, just wait for a while, you will get it. So uh, I'm going to move down if this case occurs, second one. And if the third case occurs when your target is less than array of ij, I'm going to move left. I'm going to move towards this direction. So what I'm going to do, if I have found the solution in the first case, I'm just going to return true here. And in this case, I'm going to move down. So I'll do row plus plus. And in this position, and in this case, I want to move left. So I'll do column minus minus. Now, how does it helps? Let me show you. The whole code is you want to return a boolean whether your target exists in this array or not. Let's say the function name is search and it is taking n by m matrix and a target. What I'll do is I'll create a variable to track rows and I'm going to create a variable to track columns as well. And I'll start column from the upper right corner, so it will be matrix 0 dot length, because I'm taking the length of the first row and uh, I mean the last index of the first row. So now while iterating, I am moving by row I'm moving down and by column I'm moving left. So I should be careful about not exceeding the number of rows. So rows should be less than matrix length and columns should be greater than equal to 0, because I'm moving left with the column variable. So I should be careful if I do not cross the 0th index, which will be last while moving left. So what I'll do is I'll compare the current element. Current element is at mat row column. And there can be a case when I have found a solution and this current element is equal to target. Now in this case, I'll just return true. And if my current element matrix of row column is less than target, If it is smaller, then I need to look for in the next row, so I'll increment the row. And else, the last case is when your target is smaller than current element. So in this case I'll move left, so I'll do column minus minus. And in the whole process, if you do not find your answer, just return false after completing the loop, and it means that the array do not have your target variable. So this is a very interesting code of searching in a 2D array, which takes log of m into n number of steps, where m is the number of columns and n is the number of rows in your matrix. So I want you to iterate it. I want you to do a dry run to it. It's a very interesting one. So let's say you have 1, 3, 5, 7, 10, 11, 16, 20, 23, 30, 34, 60, and you're looking for 34, let's say. Now we are starting from here, from the right upper corner. Now I'm going to, now the target, let's say, is 34. I'm looking for the target. I'll compare the target with 7, and the comparison is the target is greater than 7. So when we have this case, when your target is greater than the current element, we move to the next row. So we move here, and now our current element is 20. Now we compare target to this. Target is still large, so we move to the next row. Now we compare this to the target again, and now the target is smaller than the current element, so we move left, and now you have found the solution. So this is how it is working. So that was it about searching algorithms. I hope you find it useful, and if you do, like this video and subscribe to the channel.